Okay, so think about this for a second. Our entire universe, with its billions upon billions of galaxies, how did all of this get here? What if I told you we could actually watch it happen? Today we're diving into how scientists can build an entire universe right from scratch inside a supercomputer.
Just take a look at this. I mean, your first thought is probably, wow, what a great photo from the Hubble telescope, right? You can see the spiral arms, that glowing core, all those little pockets of new stars. But here's the crazy part. It's not real. This galaxy was born, it lived, and it evolved entirely as data inside a machine.
And that really gets to the heart of the matter. The question isn't just about this simulated galaxy. It's about the real ones, including our very own Milky Way. How did any of it come to be? That is the fundamental mystery that these incredible cosmic simulations are trying to help us solve.
So, you might be wondering, why go to all this trouble? Why dedicate these massive, expensive supercomputers to building virtual cosmoses? Well, the answer is actually pretty simple. We kind of have to. It's our only option.
I mean, think about it. We can't exactly set a timer for 13.8 billion years and wait around to watch a galaxy form. When we look out into space, all we're seeing is a single snapshot in time. A simulation, though, that's like the ultimate cosmic laboratory. We can set up the conditions of the early universe, press play, and watch billions of years fly by in just a few months. We can even go back, change the rules, and see what happens differently.
And that right there is the key. As this quote gets at, these simulations aren't just for making these jaw-dropping visuals. They are the single best scientific tool we have for testing our deepest theories about the universe against the actual real-world data we get from our telescopes. All right, so if we're going to build a universe, we need a recipe. And just like any recipe, you have to start with your list of ingredients. But let's just say our universe's ingredient list is a little strange. So this is it. This is what our universe is actually made of. And here's where it gets absolutely wild. Everything we can see, everything we can touch, the stars, the planets, you, me, all of it. That's all crammed into that tiny 5% slice of what we call ordinary matter. The other 95%? It's made of two things we can't see and we barely understand: dark matter and dark energy.
For our universe recipe, the most important structural ingredient is dark matter. The best way to think about it is like an invisible scaffolding. It doesn't give off any light, it doesn't interact with anything except through gravity. And it's that constant gravitational pull that acts as the backbone for everything else.
And this slide just shows that idea perfectly. You're seeing how that invisible web of dark matter acts like a skeleton for the cosmos. Then, the ordinary matter, the gas and the stars that we can actually see, gets pulled in by gravity, and it gathers along those filaments, lighting them up like decorations on some kind of cosmic Christmas tree.
Okay, so we have our ingredients, now we need the blueprint. You see, every simulation has to start somewhere, and for the universe, that means we have to rewind all the way back to the dawn of time.
As far as we can tell from all our evidence, right after the Big Bang, the universe was incredibly uniform. The matter and energy were spread out almost perfectly evenly everywhere you looked. It was pretty much a blank slate.
But that word almost is doing a lot of work there. Because in that near-perfect smoothness, there were these minuscule random ripples, tiny variations in density that were left over from quantum physics. And these little ripples, well, they turn out to be the most important part of the entire story.
So what happens when you let those tiny ripples sit for a few billion years? Gravity takes over. The areas that were just a tiny bit denser start pulling in more and more matter, and the emptier regions get even emptier. And those tiny random seeds eventually grow and stretch into this, the magnificent, sprawling cosmic web we see today.
So, we've got our ingredients, we've got our starting blueprint. Now for the really fun part. We just need to plug in the laws of physics and let the computer run, fast-forwarding through 13.8 billion years of cosmic history.
The whole process basically happens in two big stages. The first part is, well, it's not easy, but it's the more straightforward bit. You just calculate how gravity pulls all that invisible dark matter together into that web-like structure. It's a massive calculation for sure, but the physics is pretty simple. It's all about gravity.
The second part, though, is where it gets incredibly difficult. This is where you have to simulate all the baryonic physics, which is really just a fancy way of saying all the normal stuff we can see and touch. And here you have to model everything. how gas cools down and collapses, how stars actually ignite, how supernovas and supermassive black holes blast energy and material back out into space, not to mention things like magnetic fields and cosmic rays. It's this unbelievably complex and messy galactic ecosystem.
So after all of that, after all those mind-boggling computations, all those virtual eons passing by, what do we get? What does our finished, virtual universe actually look like?
And here it is, the payoff. On the left, you're looking at a gallery of galaxies that were literally born and raised inside a supercomputer. On the right, for comparison, we're talking about real galaxies we see in deep space. Just look at them. The variety, the structures, those beautiful spiral arms, the resemblance is just breathtaking. It actually worked.
But here is the most crucial point to take away from all of this. Getting these beautiful, realistic-looking galaxies is not the end goal. The beauty is really just a byproduct. The real success is what this incredible similarity means.
The fact that our simulation, built from our standard recipe for the universe, what scientists call the Lambda CDM model, can spontaneously produce a universe that looks so much like the real thing, that is a powerful, powerful confirmation. It means our fundamental understanding of the universe's ingredients and its rules is remarkably accurate. We're on the right track.
And that leaves us with a really fascinating final thought. We've shown that our recipe works, but we still don't know what the secret ingredients, dark matter and dark energy, actually are. So the next frontier for this work is to use these virtual universes as laboratories, to start tweaking the properties of those dark components, to see if we can finally unlock the deepest mysteries of our very own reality.